title is Free Noncommutative Hereditary Kernels, and I'm talking about decomposition as a sum of positive objects in general. And for the case of noncommutative hereditary kernels, it's the positive objects are what's called completely positive noncommutative kernels, and there will be some applications along the way as advertised in the abstract, if anybody got through all that. So the motivation, the first case is embarrassingly elementary. You take a complex number, you can write it as a real and imaginary part, which are real numbers, and a real number is either positive or -1 times a positive, so that gives you an additive decomposition into positives. Then less elementary is you take a complex measure, and there's a Hahn-Jordan decomposition, which we all teach in real analysis, that any complex measure can be decomposed as a linear combination of positive measures. And then more sophisticated, well, about the same, bounded linear operator in a Hilbert space can be decomposed as a linear combination of positive self-adjoint operators. So this is a general theme. Then in operator algebra theory, we have Wittstock decomposition theorem for a completely bounded map can be written as a linear combination of completely positive maps. So I won't define all those terms now. Either you know them or you don't, but you can. But another remark is that the Wittstock decomposition can be considered as a generalization of the Hahn-Jordan decomposition. This is explained in Paulson's book. You take the special case where the unital C-star algebra is continuous functions on a compact Hausdorff space, and your completely bounded map is take a function f, continuous function integrated against mu, and then Wittstock says you get this linear combination of completely positive maps, but a completely positive map in this case is the same as a positive map, which is given by integration against a positive measure. So then you have it. Then still more examples. Example 5, we talk about kernels as in the 1950 paper of Ehrenschein. We can take an adjoint of a kernel defined by taking the adjoint of the thing with the arguments interchanged, and K is Hermitian if it's equal to its adjoint, and it's positive if this positivity condition, which defines a positive kernel on subset omega, then it's a theorem of Moore. I've been calling it Kolmogorov decomposition for years, but I just read the new book of Agler McCarthy Young. It's really a theorem of Moore. A kernel is positive if and only if it has a Kolmogorov decomposition. And what Kolmogorov had was it's actually covariance matrix representation for a stochastic process, which is indexed by the points of the space. So from the point of view of Moore, it's just this factorization. And it goes the other way. If you have this factorization, it's easy to see that the kernel is a positive kernel. However, so if the number of points in your point set omega is finite, then it's easy to see you have decomposability, because then you can think of the list of points out and form a cap n by cap n matrix, which we can then view as a operator on cap n copies of our Hilbert space Y, and then that fits into example 3. So you just have decomposability holding by finite dimensional spectral theory, as was written on the slide for example 3. However, when there are infinitely many points in omega, it is still easy to decompose K as a real plus I imaginary part, but it turns out decomposability fails. You can't take a Hermitian thing and write as a difference of positive definite kernels. And this is a construction of Laurent Schwartz from 1964. And Alpay rewrote it in crane space language. And this is a hard technical result. You use all kinds of fancy, subtle things about linear topological vector spaces and chasing down, trying to make something, identify a completion, which doesn't work. So, in infinitely many points, it just doesn't work in general. Then we come to, however, if we have holomorphic kernels. So also in the same paper of Alpay, if you have a matrix valued Hermitian kernel, and it's holomorphic in the first variable and conjugate holomorphic in the second variable, and you have power series representation representing it on your neighborhood of zero, then you can get by with power series computation and exhibit K as a difference of two positive kernels. So decomposability does hold. Still more examples. BBLS stands for the paper of Pareto, Bott, Liebscher, Skida. And they took the next step on kernels by adding an argument coming from a C-star algebra A. So the way I'm formulating it, you have a point set omega, C-star algebra A in the Hilbert space Y, and you have a function which takes two arguments from the point set omega, but instead of going to L of Y, you have an extra variable. It maps, the values map C-star algebra A into operators on your Hilbert space. This is my simplification. They actually had another C-star algebra B instead of L of Y, and then you get into Hilbert module business. You have inner products which come from the C-star, which take values in the C-star algebra B. So I think it's enough here to keep at the Hilbert space level, and I take the second C-star algebra to be operators on Hilbert space Y, so it fits with what we've done before. So the notation is you K evaluated Z and W, then you still have to evaluate that at an element A of your C-star algebra calligraphic A. And the answer you get is an operator on Y. Then that's it for a BBLS kernel. Then we say such a kernel is completely positive if this positivity condition holds, which is the same as we saw before if you ignore the A's. So now you have this extra argument AI star AJ. So this was important for their applications, which was all kinds of fancy operator algebra stuff. But what's cute is there's a, Kolmogorov decomposition characterization. So the characterization is quite definitive. Such a kernel is BBLS completely positive if and only if there's another Hilbert space X, a star representation of your C-star algebra A into operators on X, and a function H from your point set omega to operators from X to Y, so that KZW of A has this factorization with the representation applied to A in the middle. So H of W star goes from Y to X. Pi of A is an operator on X. H of Z takes you X back to Y. So this decomposition, you plug in this decomposition into this condition, and it all works out that this condition holds. So that's neat. So then we can ask the same question. Uh, we have, I didn't say, we have a notion of real here also. So you can decompose a general kernel as the real plus I times a real, linear combination of reals. And then the question is, can you decompose a real as a difference of completely positive? But first, I want to give all the connections. How are Ehrenstein kernels related to BBLS kernels? Well, if K is a BBLS kernel, for the special case, your C-star algebra is just complex numbers, then you form lowercase k by plugging in 1 into the operator algebra argument, and then that's going to be an Ehrenstein kernel. Conversely, if an Ehrenstein kernel, you can form a new kernel, which we view as values or operators from C to Y by just scaling by the C, then such a K will be a BBLS kernel. So the Ehrenstein kernel is, if you like, the special case of BBLS kernel where your operator algebra is just complex numbers. So from what we've already been through for Ehrenstein kernels, if the number of points in omega is infinite, we see that decomposability will fail. The fact that it fails for Ehrenstein kernels means that it also fails for BBLS kernels, because Ehrenstein kernels are just a special case of BBLS kernels. Just as is the case for Ehrenstein kernels, if the number of points in omega is finite, then decomposability does hold. And this is a fairly substantial paper of Bhattacharya, Twitchell, Todd, who carefully worked all this out and had difficulties with the infinite point case, but they had a bootstrap condition, which when it holds, then you can get decomposability in the infinite dimensional case, infinite point case. But my topic is noncommutative kernels, which is a fairly intricate object. So I begin with noncommutative functions. And noncommutative functions have been around for 10 years or so. There have been lots of talks. And I'm sure many in the audience have given or been at some of these talks, but I'm not assuming that everybody is familiar with noncommutative functions. So I'll do a quick overview. Apologies to the experts. So I'll take V as a vector space, then the non-commutative or quantized version of V is to take all square matrices over V, all possible sizes. And sometimes we even take rectangular matrices over V, all possible sizes. Then a key point is we want to multiply on the left and the right by matrices over complex numbers. So in fact, the vector space is a modular over complex numbers, means you can multiply on the left by matrix over complex numbers and on the right by matrix over complex numbers as long as the sizes fit. So we use these operations all the time. So alpha is K by N over C, Z is N by M over V, beta is M by L over C. Then alpha times Z times beta, K by L over V makes perfectly good sense. And I'm going to take omega is going to be my point set, and it sits in this the subset of matrices over V, all possible square sizes. And then I'll have occasion to talk about noncommutative envelope, which means you have to throw in all possible direct sums with diagonal entries from omega. And then we want to talk about noncommutative functions. So we'll take V0 as another vector space, which is going to be in the noncommutative expansion of V0 is going to be the space of values for F. F is defined on some domain, which is not all of VNC. Then we say it's a noncommutative function if it's graded. So if you're the Z in the domain is at level n, then F of Z, the value, is at level n in the range space. So level n of the range space is M by N matrices over this other vector space V naught. And it should respect intertwinings. So if alpha is MIN over C, Z is MIN over V, Z tilde is another point, which is M by M over V, then alpha Z equals Z tilde alpha makes good sense, where you're using V is a module over C, and alpha F of Z and F of Z tilde alpha make perfectly good sense because of the right size, but now you're using that the vector space is V naught, so you need this identity. So it preserves intertwining. Intertwining in the domain forces intertwining in the range. And then it's useful to know that respects intertwinings actually can be broken up into a pair of conditions which together are equivalent, preserves direct sums, and preserves similarities when you have an invertible MIN matrix. And this goes back to Joseph L. Taylor in the 70s, who was trying to figure out functional calculus for functions in non-commuting operator arguments. So he had, these are the axioms that should be satisfied. Now we need examples. So the first example is polynomials. So we need F is for free, unit of free monoid on D generators. So the elements of this gadget are words in the generator. So you take a word in the letters, 1 to D, and that's your element of FD plus, and we throw in the empty word, which acts as the unit. And we have multiplication and juxtaposition. Then to have functions, we'll first start with a tuple, D-tuple freely non-commutative indeterminates, which are the fractor little z's. Then formal free monomial, the power is a word. You take the collection of indeterminate z raised to the power, the word fractor a. Then you take the letters in the word and put them as subscripts on the indeterminates. So you get this monomial in z, but the order is important. Then a formal polynomial, formal polynomial is a linear combination of monomials. And it being a polynomial means only finitely many of the coefficients are not zero. And here I'm thinking of the coefficients as complex numbers, but they could be whatever you like, operators on some space, or well, usually some linear space. Then formal polynomial is a non-commutative function. We want to make a substitution for the variables by operators. So I'm used to taking, we'll take V to be d-tuples of complex numbers, and then n-tuples of square matrices over d-tuples can also be thought of as a d-tuple of square matrices. And this is convenient when we're thinking of functions. So we take a d-tuple of n by n matrices, more generally, d-tuple of operators on a Hilbert space, and the multiplication is ordinary operator composition instead of juxtaposition. So we have a functional calculus given a tuple of square matrices. You plug it into the formal noncommutative polynomial, and out comes another operator with this formula. And if the PAs, so here the PAs are, say, operators U to Y or something. And then tensoring makes them n by n matrices over operators U to Y, and so on. And then if they're just scalars, we could omit the tensor and just think of it as a scalar multiplication. So that's our first example of noncommutative function. And then the point is, it satisfies all these axioms. That's basically the example where you get all these axioms satisfied. Then if we want more examples, there are various, what's most convenient for this talk is just to talk about convergent power series. So we have some kind of noncommutative Reinhardt domain. So there's a radius of convergence, and we consider all z's for which the power series converges on some domain of interest. And that'll give us, then the result will again satisfy those gradedness and respects intertwining. So this is how we get examples. And this is noncommutative Reinhardt domain. Now, if you take a more general domain, it's not clear how you write such things down. It's hard enough in commuting variables where you have to use Taylor functional calculus or something. I believe there's no non-commutative version of Taylor functional calculus, but people are working on it. Then this turns out to have strong holomorphicity properties. If you're on a open set in non-commutative d-tuples complex numbers, and it's locally bounded, then there's a result in the book of Kalyuzhny, Verevetsky, Vinnikov, for example, that you restrict to a level, then the C1 to ZD involves d times n squared parameters, then you think of as ordinary multivariable holomorphic function with respect to those parameters. You have automatic holomorphicity just from satisfying the axioms and the local boundedness. So therefore, we can think of locally bounded non-commutative function as a quantized version, namely you consider it acting on matrix arguments of a multivariable holomorphic function. And the natural domain of convergence for such a power series is what we'll call a non-commutative Reinhardt domain. And one such domain where lots of work has been done is the non-commutative ball. So you take d-tuples of n by n matrices such that when you put them as a row operator, you get a strict contraction. And then the non-commutative ball is to take the disjoint union over all such levels. And that's the natural domain for many non-commutative functions. Then we want to move from functions to kernels. So a kernel is, we've seen, is just a function of two arguments. So that suggests what a non-commutative kernel should be. So again, we have a point set contained in non-commutative, the non-commutization of a vector space. A is a C, now we have A as a C-star algebra, like we had for BBLS kernels. then our kernel swallows two arguments from omega, and the result is an operator from ANC to L of Y NC, whereas BBLS, we drop the NC. So the NC means you're taking matrices. And in this case, you're taking actually rectangular matrices. Then graded means you take a point at level n, z's level n omega, w is level m from omega. Then what kind of object should KZW be? It takes as an argument n by m matrix over A and spits out n by n matrix over L of Y, which can also be thought of, and it's convenient to think of as an operator from Ym to Yn. If we want to make things more concrete. That's graded in this context. Respects intertwining in this context is we have Z and Z tilde at various distinct levels. We have n tilde by n matrix over C alpha. Intertwined Z to Z tilde. We do the same thing with the W's. Intertwined by a beta. And we have a P, which is an n by n matrix over A. Then you take this expression, has to be this tilde expression. The alpha pulls in, goes past the Z, turns into Z tilde, and hits the P. Then the beta star goes into W, goes past, turns W into W tilde, and then it comes out on the other side of the P. So it's actually the same if you introduce adjoints, as I will in a minute. And then again, you have respects intertwinings is equivalent to a pair of conditions, respects direct sums, respects similarities, which is all this mess, which you aren't going to absorb immediately the first time you see it. So I just thought of the informal definition, which perhaps makes it more plausible. We have a function from omega cross omega to operators from, well, it's A noncommutative, L of Y noncommutative, should be. And what does it mean to be a noncommutative kernel? It means that it should be a noncommutative function in the first argument. So by that, I mean we fix the second argument, but there are all these arguments around here. So I'm going to fix the W naught, the point at level M and omega. I'm going to fix A naught, which is a column over A, M entries. I'm going to fix Y naught, the column over Y, M entries. Then I'm going to use these data to define a noncommutative function, as we've had before, from omega, and the vector space it goes into is linear operators from A to Y, and I take square matrices over that. And the formula is, given a Z and omega n, A and AN, that's where it should be, then this formula gives you what it is. So you can check, this is a noncommutative function. So I use here that n by n matrices over LAY is the same as linear operators from AN to YN. So you take A as an AN, you apply F of Z, Z was an omega n, the answer is in YN. Then the fact that K respect intertwinings. So take beta as the identity, take W equal W tilde, that's fixed to be W naught. Then you tangle through all this, and you will get that this object is a noncommutative function. So that's natural. In the first argument, it's our quantization of actually a holomorphic function. Then noncommutative function in the second argument, we get less tangled up if we take the dual. We take the dual kernel. You interchange the arguments, replace A with A star, take the adjoint of the whole thing. Then the condition is that this dual object is a noncommutative function in its first argument. Then again, you see what that means, and it just means you go through all this with alpha identity z equals z tilde fixed, and the beta and w tilde. Doing this is exactly what it takes to get this to be a noncommutative function as first argument. So the heuristic is a noncommutative function is a quantized version of a holomorphic function, and a noncommutative kernel is just a quantized version of a sesquiholomorphic kernel. So there are applications, as maybe we'll see, but it makes good intuitive sense also. So for examples, we build them out of noncommutative functions. So I took the Agler hereditary kernel, noncommutative version is we take noncommutative functions, so a whole bunch of them, FIGI, and they land in operators from A to L of Y, and you take square matrices over that, which is the same as operators from n copies of A to n copies of L of Y. N copies, okay. And you find K with such a formula, arbitrary sum, then this will be a noncommutative kernel. And more generally, you could have an integral of such things. So this is a noncommutative version of Agler's hereditary function. The stars always to the right, and the P in the middle, and unstars with the Z on the left. That's how I do it. So we're interested in what's going to be the positive object in this category, and that'll be completely positive noncommutative kernels. So it's just the next step after BBLS. K is completely positive noncommutative kernel. If K is a noncommutative kernel, and it satisfies this positivity condition. So at level 1, it's exactly the same as for BBLS, but now we have to have matrix arguments of all their individual sizes, and the A's have their individual sizes. So A's are tall, so this is, and AJ star is a row. So this AI AJ star has size NI by NJ over A, which is the right size for it to make sense when ZI's level NI, ZJ's level NJ. And then you hit it on vectors of the right size, and this whole thing is should be non-negative. Then there are equivalent formulations. If K is extended to the noncommutative envelope, then because you have all this freedom of throwing in more direct sums, and you use preserves direct sums, then you have these simpler conditions can hold. Then we have Kolmogorov decomposition for this, which should look familiar now. You have noncommutative kernel, then it's going to be completely positive exactly when it has this noncommutative Kolmogorov decomposition, which means there's an auxiliary Hilbert space X noncommutative function H from omega to square matrices over operators from X to Y, unital star representation pi for your C-star algebra A going to operators on X, so that for arguments Z and W, level N and M, P n by n matrix over A, KZWP has this factorization. So you see here, P is n by m over A. Identity n by m tensor pi means you just apply pi entry-wise. Then everything fits. The result is a m by n matrix over operators on X. So that's an operator from m copies of X to n copies of X, which is exactly what you need for this to fit. And then you land an operator from Ym to Yn. So that's our completely non-commutative, completely positive kernel, Kolmogorov decomposition. That's all it is. Now, connections with other objects. If we assume omega only has level 1, and we take C-star algebra A to be complex numbers, not a very exciting C-star algebra, but nevertheless, and we have a completely positive non-commutative kernel, then we define K by restricting the C-star algebra argument to be 1, then that's an Ehrenstein positive kernel. On the other hand, if, oh dear, if we suppose everything's at level 1, and furthermore, there's only one point. So K, there's only X on only one point, and you end up in operator from the C-star algebra A into operators on Y. Then we set phi to this map, K evaluated Z0, Z0. That's the only place you can evaluate it. You get a map from A to L to Y. Then the original K is a completely positive non-commutative kernel, if only if phi is a completely positive map, which I didn't plan to define. I think most people know completely positive maps. And then furthermore, the Kolmogorov decomposition for K, the big K, collapses to just the Steinspring representation for phi, which means that for A in the C-star algebra, phi of A has this representation. V, as I forgot to say, is an isometry. And it's not S, it's X. I was getting tired here. V is an isometry from Y into X. And then pi of A, pi is a representation from C-star algebra elements to operators on X. So everything is correct if you change S to X. So the Kolmogorov decomposition for the completely positive non-commutative kernel just collapses to the famous Steinspring representation for a completely positive map. Then if we suppose, on the other hand, all the points are at level 1, we make the point set as part of a vector space. We consider the points in omega to be linearly independent, just for technical, because we had to have a vector space. Then suppose we have a K from omega 1 cross omega 1 to operators from A to L to Y. Then K is completely positive non-commutative kernel is exactly the same as K is a completely positive kernel in the sense of BBLS. So everything fits together. Everything's connected. So the moral of the story is completely positive non-commutative kernels generalize everything. So in order to talk about how much time, still cooking. Um, now get back to the decomposability problem. To discuss the decomposability problem for non-commutative kernels, I want to discuss another way of looking at them. So if we take the finite point case, omega is just finitely many points, contained in the ambient non-commutative vector space, and we have a function k from omega cross omega into operators from non-commutative A to non-commutative L and Y. So there are only finitely many points. Z upper zero is the direct sum of these finitely many points. And each Zi has size Ni by Ni. So Z0 has size big N naught, cap N naught by cap N naught the sum of the little n's. And we can organize Z naught as a block n by n matrix with blocks of size, block ij of size ni by nj. And then we can, given our non-commutative kernel K, we can define a, what did I say S was? Forget S. S is, oh, that's supposed to be A. I had a notational problem. So it's supposed to be blackboard bold A is n naught by n naught matrices over the C star algebra A. And so you're going to have a map from this C star algebra to blackboard bold L, which is n naught by n naught matrices over operators on Y. Namely, you take P, which is just this big matrix over A, and you map it to K Z naught Z naught. The only thing you plug in the arguments of K are Z naughts, and you evaluate that on P. Then by the preserves direct sums property, you get this block matrix for the answer. And then the goal is to translate properties of K, which was our non-commutative kernel. We wanted to relate it to, or a completely positive non-commutative kernel, to properties of this map phi, which is just with algebras, operator C star algebras. It maps this big C star algebra to this big C star algebra. Then what can you say? What happened? That doesn't work anymore. But
okay.
So the solution, take S to be, that's what S is, n naught by n naught matrices over C, and restrict to those alpha for which alpha Z naught equals Z naught alpha. Roughly the commutant of Z naught in n naught by n naught matrices over C. Turns out this is a subalgebra of n naught by n naught matrices over C, but it's not a star subalgebra. Let us say phi from blackboard bold S to blackboard bold L is a bimodule map if this bimodule property holds where alpha and beta are in S. So beta star may not be. So it's a SS star bimodule map is how we say it. Then the result is K is a non-commutative kernel exactly when phi K, a map from matrices over C to matrices over matrices over C to matrices over LOI is a SS star bimodule map. Converse, if you have a phi, just takes this C star algebra, this C star algebra, then it's an SS star bimodule map, then it comes from a noncommutative kernel K. So that gives us a tool for understanding noncommutative kernel. Now it's back again. It's a bit of a story. Well, that slide should have gone before the previous one. So that's the result. I think I did things in the wrong order because I'm having these problems. And there's a converse to the theorem. K is completely non-commutative kernel if and only if phi k is an SS star bimodule map. So now you add completely positive. So completely positive on the one side is the same as completely positive on the other. So we have a translation. We get rid of kernels and we have maps between C star algebras. That we already did. Conclusion, theorem continues, then there's an equally determined. I have to look, oh, I can go here. Then for this to work out, we get it to work out if we assume something extra. Our subalgebra S should have the complete spectral factorization property, which means you take a square matrix over the C star enveloping algebra of S, which is positive. You have to be able to do a so-called spectral factorization. You have to factor it as beta beta star with beta in the algebra S. So if S is upper triangular matrices, that's no problem when n equals 1. But you have problems when n is bigger than 1. You can do this when S is the disk algebra or H infinity of the disk, but that's not what's coming up here. And the easiest example which has this property is S is already itself a C star algebra. And then the theorem is that if you have this property, then we can solve our decomposability problem. So that was the moral of the story is decomposability holds if you have finally many points. Decomposability, it appears, fails even when you only have finally many points. Then there was a connection with, that was that. Never going to pick interpolation, but I'm going to run out of time, am I not? So quickly, here's the non-commutative never pick interpolation problem. We have a Q disk and we have functions. We have to take omega prime to be a certain extension of omega intersected with the Q disk. And we have non-commutative functions A and B on this extended set. And we want to find non-commutative function which takes the whole Q disk into matrices over operators U to Y so that AZ SC equals BZ. That's the wrong direction. That's 21. So here's the solution from our paper 2018. So here non-commutative kernels come up. So you have, there's a solution to the interpolation problem. And on this extended set omega, just a straight positivity condition with single argument z. And 2 is that just on omega, not omega prime, we have what Agler-McCarthy call a model, we call Agler decomposition. So you have this kernel, it should be represented as factored through a completely positive kernel, gamma, and you have this kernel inside the argument. And furthermore, then S can be given a transfer function realization. Then the here's the discussion. In particular, I want to focus on 1 prime if and only if 2. Here's 1 prime repeated and 2 repeated. Then 2 implies y prime, at least on omega, is easy, because then you just restrict p to be the identity and it takes z equal to w. Then 2 implies 1 from, if 1 omega is strictly considered in omega prime, it's not obvious how you go from 2 to 1 prime. So 1 prime to 2 is the non-trivial direction which takes along cone separation argument. But this suggests a positive Stellensatz. Namely, if omega were equal to omega prime, then you have condition 1 prime, and this condition 2 is the certificate for why 1 prime should hold. So this suggests a reformulation as a positive Stellensatz. We define a kernel like this, a new kernel Q, define a new kernel fractor S, this. Forget where it came from, consider these as non-commutative kernels. In fact, these are decomposable non-commutative kernels. And 1 prime and 2 in this notation becomes, we're assuming this guy is positive semi-definite, evaluate on the identity here, and the same point, ZZ here. And the certificate is there's a completely positive non-commutative kernel K, so that KZWP, a much more elaborate thing, factors through the completely positive kernel with the Q. So when you take P equal to identity, Z equal to W, then condition 2 becomes condition 1 prime. You read it off. That's what I say here. So does this if and only if hold for more general non-commutative kernels Q and S? And the answer is yes, with some hypotheses. So kernel, we call it kernel dominance theorem. You have C is a full subset of non-commutative V, which means it has some extra properties I won't go into. You have fractoric Q is a Hermitian non-commutative kernel. We have to assume that it's decomposable for any finite subset of C. And we have the positivity set of Q, the set of points Z, where you have this strict positivity condition holding. we take omega to be a subset of the positivity set of Q. Omega prime is this extension of the positivity set where you add, it's sort of a non-commutative Zariski closure I won't go into. Then you have S is defined on omega prime cross omega prime is a non-commutative kernel, and it should be decomposable for any finite set of omega prime. Then indeed, we get a result. One prime kernel implies two kernel, and if omega equals omega prime, then they're hold if and only if. And the non-commutative left tangential Nevelina-Pick interpolation setting, we had only the gamma 1 appearing. And the second term, for special reasons, you can get rid of. Then this is of the same flavor as clean positive Stellan-Jot's problem, given Hermitian non-commutative kernels. And you assume on C that when this is positive semi-definite. That's this kernel dominance property. Then the problem is to find completely positive non-commutative kernels so that we have this decomposition for S. And this is the fits into the framework of non-commutative positive Stellan-Zeta, Helton, Klepp, McCullough, where you have to assume Q and S are matrix polynomial non-commutative kernels of such a form. And the positivity set should be bound in the norm. You have to add Archimedean hypotheses, and then it fits into this kernel dominance framework, which comes out of our non-commutative Nevelina-Pick interpolation theorem. And James also discussed extensions of this to rational non-commutative functions, which he can explain better than I can. And I'm done. Thank you for your attention.